Hey, I'm going to do some notes for you about this KR is the rotational variety of kinetic energy, and moi, which means me in French. No, just kidding. It's not really that. This is an initialism. Just say this M.O.I. This is the moment of inertia, also known as rotational inertia. It's called both those things. Both right. In physics, kind of like the word normal in physics means perpendicular. So that's like a special science meaning. Moment also means like a moment arm is like rotation. So the moment has to do with rotation in physics. Look it up in the dictionary. I should have done that before I made these notes so I could tell you what exactly it says. But go ahead and look that up. It's definitely like far, a few ticks down in the different definitions of the word moment. But it should be there. All right, so kinetic energy of rotation and moment of inertia. I have to tell you, this is one of my favorite little bits of notes to deliver because it is such a wonderful example of how we don't decide, we people who are interested in doing physics, once we have like the most basic definitions of, okay, this is how we're going to define position of something, and then its velocity is the change in position with respect to time and acceleration, and then so on and so on. And really, mass is, if you like, force is by definition the the thing that causes acceleration to happen. Anyway, everything falls out of, we're not just going along like making things up. In other words, once we start measuring things and observing the world, the universe around us, these things suggest themselves. Like, remember where kinetic energy came from in the first place. You can go back and revisit those notes if you want to. But anyway, blah, blah, blah. I want to show you how this all plays out. So let's say we have an object. I'm going to make it not just like a perfectly round kind of thing, because it does not have to be that. And let's say it's rotating on some axis. And let's say it's rotating in the counterclockwise, that's usually what we consider to be positive direction, with an angular velocity of omega. Now, if you've ever been around a one of these high efficiency washing machines, you ever seen one of these things? When it starts doing the spin cycle to spin those clothes to try to get as much water as it can out, boy, those things spin pretty fast. And although it's not going anywhere, I mean, that's not like the whole washing machine is like, or so sometimes they rock enough that they sort of vibrate across the room if you're not careful. But assuming that it's standing in place there, it's not going anywhere. It doesn't have any translational kinetic energy, but boy, that thing spinning really fast, it does have a lot of energy. And it's the kind that it has is rotational kinetic energy. So that's definitely a thing. There's a great picture, little anecdote in your book that you should look at about some kind of facility. I can't remember what the machine was, but they had something that was designed to spin really, really fast, but there's some kind of imperfection in it. And it exploded, basically, only because of, not because there was any explosive charge, just all of the energy of the rotation of this machine was released, and it just destroyed the entire building that it was in. Or busted through some walls, at least. So if you have an object like this, any object that's rotating on an axis, there is kinetic energy associated not with its moving from one place to another, but from the rotation. So how are we going to try to figure out how to deal with this? Well, we're going to go back to things that we know. So let's just take a small little piece of this thing. Let's say the piece right here. And let's say that this piece has a mass, I'm going to call it M sub I. Right? I for like an index variable that could be like 1, 2, 3, 4, 5, 6, all the way up to however many little pieces you chop this thing into. And this little piece is small enough that instead of thinking of it as like a rotating object, I could just think of this as an object that's moving, right? So let's say that it's at a distance from the axis r sub I. Right? Well, what's the kinetic energy of this piece? I'll call that K sub I. What is the kinetic energy of that little piece? Well, it's 1/2 the mass of that little piece times its speed. I guess I could call that V sub I squared. And now what is the speed of that little piece? Well, I know that if I have a regular old velocity, that is equal to the speed of something. The relationship between the rotational variables and the regular old variables is that this is r times omega. Right? We know that from our first set of rotational variable notes, which I'm kind of looking around here. I have those somewhere, and they're not too far away. I'm just going to flash those in front of the camera. Oh, there. Sorry, I didn't mean to bump the iPad there. But remember this. You have these your rotation notes that because of really the definition of what radian measure is, that if these things are changing with time, then we can just take the derivatives of that, and V is equal to R times omega. So, of course, here we're talking about this particular VI is equal to R I times omega. So I could substitute that out here, and the interesting thing about this that we want to observe right now is that although all the little pieces, if we chop this up into a lot of pieces, they all have different speeds depending on how far away they are from the axis, but they all have the same omega. They're all moving with the same radians per second. So some might be moving faster because they're further away from the axis, but in terms of like the whole object like makes one whole rotation. So all the bits of it have the same omega. Where they don't all have the same V. So that's important for us to recognize. That's one of the reasons we want to have these rotational variables in the first place, because we can talk about like the rotation of the whole object and not have to talk about positions and velocities and accelerations that are all different for the bits of it. Okay, so let's make that substitution. That's a weird order of words, so we should say that, since this, and then we can say then. That's the right connecting word. Then our kinetic energy of that piece is equal to 1/2 m sub I, and then we're going to substitute this r sub I omega squared. All right, and the omega is the same for all of them, and then so I'm just going to rewrite that a little bit. That 1/2 m sub I r sub I squared omega squared. And then what if we wanted the total kinetic energy of the whole thing? So if you chopped it up into lots of little bits, then you just have to add up all the bits, right? If this one has that much kinetic energy, then these other bits, you know, kinetic energy, none of it's going to cancel, right? Energy is not, it's not a vector. So you're just piling up more kinetic energy. So it would just be the sum. And sometimes when we do these sums, we just put this I right here, which just means the sum over all the different values of I. Instead of saying I equals something to something, this just means the sum of all of the bits. So the sum of this expression here, of the 1/2 m sub I r sub I squared times omega squared. But notice that the 1/2, of course, that's a constant, and the omega is the same for all of them. So those things don't have to be inside the summation. They can be factored out. So 1/2 the sum of all of the M.R. squareds for all the different bits times omega squared. Okay, so a couple of observations here. If you think about what regular kinetic energy is 1/2 mv squared. And this rotational one is coming out to be 1/2 this times omega squared. And omega is angular velocity. So this thing right here, let me just write, I think you should probably have this in your notes, like 1/2 mv squared. So there's a real strong suggestion to us here that if there is such a thing that we're going to talk about that's like rotational mass, that this is what it should be, right? Because this is 1/2, whatever that is, times omega squared, and kinetic energy is 1/2 mv squared, so this must be the rotational analog of mass. And in fact, that is exactly what we're going to do. We are going to call this let's see. This is how we make definitions in physics. We just don't go along saying, oh, rotational mass, let's make it this, and just come make up some crazy thing for it. We let the physics, let the math tell us what to do. So we're going to define the rotational inertia, or moment of inertia, which is the same as the rotational inertia. We're going to let that be equal to the sum of all of the M.R. squareds. Now, if all you have is one particle, then its rotational inertia is just M.R. squared, right? So, for example, what's the rotational inertia of the Earth as it goes around the sun? The Earth is far enough away from the sun that you can treat it as a particle. So it would be the mass of the Earth times the radius of the Earth, the radius of that circle in 1 astronomical unit, about 93 million miles squared. That's how you would do that. So, I mean, if you're wondering, remember the problem that we had about a boy was like swinging a rock on a string? If you wanted to know what's the rotational inertia of that rock as it moves in that circle, you would do just mr squared for that rock, because the rock is basically just a particle. But if you're talking about an object that has like an axis going through it, like a solid object rotating like that, well, then you got to chop it up into a bunch of bits like this. And if you chop it into infinitely many bits, or you let the number of bits, you let I approach infinity, then the rotational inertia, I, is equal to the integral r squared dm. Because the mass, the little tiny, tiny masses that you're chopping it up into, those are going to approach, just like when you divide up, when you're doing a Riemann sum, the width of those rectangles approaches 0, right? So the little x's, the little delta x's turn into dx. So that's what's happening here. The little tiny masses are turning into dm. Now, this equation here is going to show up on your equation sheet. And it's kind of hard to know what to do with that. And for a long time, in my experience teaching AP Physics, For a long time, that always showed up on the equation sheet, and me and all the other AP Physics teachers of the world, were like, yeah, whatever. We're never actually going to use that. We just need to know some rotational inertias. Whatever, we won't really teach our students how to use that. And then all of a sudden, a few years ago, maybe 2017, boom, there it was on the test. You had to actually do this. So I have since made a video that explains how to do that in the particular way that the College Board is going to want you to, should they ask. And in the years since then, I think in like 3 out of 4 years, in 2017 to 2020, they have asked a question about that. So it seems to be like in their bag now that they like to see if you can do it. So I'm not going to talk about that right now. What I am going to talk about is the rotational inertias of some particular regular and common objects. So, oh, and I'm going to say one other thing first that we need to know. There's something that's called the parallel axis theorem. Which you'll see how we can use it in just a second. So the parallel axis theorem says that if you would like to know what the rotational inertia of some object is through some axis, and you know what the rotational inertia is through its center of mass, which we often do because I'm going to show you some common ones here, then to find the rotational inertia around this new axis, you just do the regular inertia around the center of mass plus mh squared, where h is the distance from the axis to the center of mass. Right? You'll have examples of how to do all this soon, like. All right, so here's some common rotational inertias. For a particle, it's moving in a circle, it's mr squared. Right? It's just one particle, just mr squared. The next most common thing that we see is a disk or a cylinder. And these are all, we're assuming that for all of these objects that the axis is going through the center of mass. Of course, with the particle, the center of mass is the particle. But for disk or cylinder, disk or cylinder, we're talking about an axis that goes through the center of mass. So for example, like here's a little cylinder. We would be talking about the axis that is right here, like right where that hook is entering it, not rotating it like on some other axis. I mean, it could rotate if you had an axis there, right? We're talking about the axes that go through the center of mass, which is a good one to talk about because if this thing happened to be like rolling, that's the axis that it's turning about. So it's usually like that sort of obvious axis. So disk, cylinder, let's see if I can spell cylinder. Cylinder, that's not hard. The disk or cylinder, it's 1/2 times the total mass of the mass of the disk, which you could just say mask, because that means mass of disk for short. 1/2 mr squared. Like, why is it that? Well, you have to do the calculus problem, and I think I might have included this example in that video that I will post. I think I'm going to post it later in the chapter, though. I don't think we want to worry about it right now. So anyway, that's coming. That's where all these come from doing calculus. But it's a little complicated, the calculus, so we don't want to get into that right now. Particle is that, disk is that. How about a hoop? Do you know what a hoop is? Sure you do. It's like a hula hoop. It's like a disk, sort of, but it's all the mass is at the very, very edge. So what's that going to do? Is that going to increase? You think it's going to be bigger or smaller than this? Well, a hoop, it really, if you think about it, it's like a collection of particles, all of which are at the full radius of the circle. So it's also mr squared, where m is the mass of the hoop, because all of the bits of it are at the full radius. So it's kind of maxed out. If you have like a round object and you want to maximize that rotational inertia, then you got to push as much mass as you can to the edge. For those of you who are familiar with rotating objects, like let's say the discs you use in disc golf, then one of the things we're learning here is if you think about the different properties that different discs have, you could think about how much this mass, how much of the mass is like forced out to the very, very edge compared to kind of like spread out more toward the center, and what effect that has on the rotational inertia. It's one of the things that if you're in the business of trying to make discs that have different properties, one of the things that you would think about. So you take out your discs and think about that, look at them, meditate on them, because they are beautiful. So particle, disc, hoop, like a bicycle tire could be considered pretty hoop-like. It's got like spokes and stuff, but the mass might be, you know, fairly small relative to the rest of it. Particle, disc, hoop, what else we got? Also need what about like a solid sphere, like a lacrosse ball? Sphere. And then there's more math to be done there. For a solid sphere, it is 2/5 mr squared. Why is it that? Because of calculus. Then how about a hollow sphere? In case any of you are ping pong enthusiasts, or tennis, or I guess basketball is pretty much a hollow sphere, isn't it? So all of those balls are hollow spheres, which have, or very nearly, right? Hollow sphere has rotational inertia of 2. What do you think the denominator is? Would it be bigger or smaller than the solid sphere? Pause. Pause. Well, a hollow sphere, the more of the mass is out at the edge. Now, it's not just mr squared like a hoop, because the solid sphere, although all the mass is pushed out as far as possible, the axis goes right through the middle, so some of the mass is actually quite close to the axis, like at the caps. Like thinking of like the polar ice cap caps, I mean. So this turns out to be 2/3 mr squared for the hollow sphere. Let's see what else. For a thin rod, and there are lots of things that you can approximate as thin rods, like if we were going to take like any kind of stick type object. So a thin rod, now this is through the center. Just going to add that here. These ones are more obviously through the center, I think. So thin rod through the center is 1/12 m. Now a rod doesn't really have a radius, so we're going to say ml squared, where L is the length of that rod. And a thin rod about the end, which is pretty common, kind of like swinging a baseball bat, or if you balance a stick. Let's see, that's too long. So if you balance something like this and you let it fall over, it's really like a thin rod that's rotating about one of its ends. So that comes up a lot. If you were doing like the bicycle tire and you really wanted to get it, like to nail it down, you could do the hoop part of it and then plus all of the thin rods that are rotating about their end, that are like attached at the center and sticking out. So thin rod about the end. How would you do that? Oh, you do the parallel axis theorem. I'll show you. Turns out to be 1/3 ml squared. That's a 3. That's a 3. So how do you get that? I'll just show you an example of this parallel axis theorem, which would say that my new rotational inertia about the end is equal to the rotational inertia on the center of mass. This is the easiest one to do with calculus because all the mass is just in a straight line. I think that example is definitely in the video that I made that you'll see later. Plus mh squared, where m is the mass of the rod, and how much have we shifted here? If you're shifting the axis from the center of the rod to the end, the center of the rod to the end is half the length of the rod. So that's L over 2 squared. Okay, so let's see, that's 1/4 ml squared plus 1/12, and let's see, 1/4 is 3/12 plus 1/12 is 4/12, which is 1/3. So that's how you do that. That's a thing you're going to have to know how to do. I think that that should do it. Maybe just a couple more things, let's see, that you need to know before you start jumping in and trying to do some problems. What are the units of rotational inertia? Well, it's an m times an r squared. So it's a mass, which is kilograms, times an r, which is a distance, squared. So the units of rotational inertia are kilogram meters squared. There's no special name for that. It's just kilogram meters squared. And the other thing, I guess, just the last word is that this is the rotational analog of mass. And just like if you have an object like a 500-gram mass, and then you put a 100-gram mass on top of it, what's the total mass? It's 600 grams. You just add them up. The same thing is true for rotational inertias. They just add up. So if you have, for example, let's see, if you have, for example, a rotating disk like this right here, and you put another object on top of it, let's see. I'll try to give you an easier example here first. So then you put another object on top of this here, and they rotate together, then you just add the rotational inertias. That also goes for things like if I put it out here. This is a little bit more complicated because now this is not rotating around that axis. So is this a cylinder? Pretty much, yes, but the axis is shifted. So you'd either have to do like a parallel axis shift to this, or just say, you know what, this is far enough from the center of this that I'm just going to treat it like a particle where its mass is at the center of mass. And that's a pretty good approximation, works pretty well. There is a classic example when we get to talking about the angular momentum. There's a classic problem where a kid comes running up toward the little merry-go-round thing at the playground and jumps onto the edge, and they start to rotate. So like that case, if it's an object that's kind of small-ish relative to the radius of the object, then we just treat it like it's a particle. So you just add them together. You got things on top of other things, add them up, just like you would do with masses. I have one of these wheels that rotates better than that one. That one's pretty friction-y. Or maybe it's just friction-y when... Let's see, another one. No, that one's worse. Oh well, we're going to fix that. Oh, that one, the axis is all off. Well, alright, I'm going to get out my hammer and try to fix that. See you later.